Welcome back. Today we're going to talk about section 2.2, which is power functions. We're going to look at what are power functions. We're going to look at some examples of them in the coordinate plane. We're going to look at some of the characteristics that make them power functions, and we're going to look at some of the interesting little quirks that just happen to happen because of the math that has to do with power functions. So here we go. A power function is defined like this. We've got f of x is equal to k times x to the a power. And it's a power function because obviously it has this power. Okay, so there's a power of x. And it also has this k here, which is a constant of variation. Okay, that's the constant of variation. And so that's going to be like a 3x squared or something like that. So k and a, little a, are non-zero constants. And so this is the basic setup for a power function. It's got some constant times x to an a power. Now the constant could be 1, the x power could be 1. And so let's look at a couple of examples to kind of help us figure out what we're exactly looking at here. The first one that we're going to look at is circumference. So for example, circumference of a circle. The formula is defined like this. C is 2 times pi times radius, pi times diameter, so 2 times pi times radius. The power, we're looking at what varies, so 2 pi is always the constant. We'll put that here. And the radius is what is varying. That's what we can put in. So the power is 1 because this is radius to the first power. If we're looking at a different example, we can look at the area of a circle, and you're going to see that the area of a circle also is a power function. So switch to blue here. Area equals pi times radius squared. Well, my power in this case is 2. My constant of variation in this case is just pi. It's the one that doesn't change. So radius is what changes based on what I put in, and the pi doesn't change though. Another example would be the force of gravity. The formula for the force of gravity is F equals K divided by D squared. And in this case, we have to know a little bit about exponents and the way that they work. When I have a squared on bottom, that would mean my power is actually -2. What we're going to talk about in a minute is inverse or indirect versus direct variation. And so in this case, because the squared is on the bottom, the power is -2. My constant of variation is still K. Another one is Boyle's law. Boyle's law is V equals K divided by P. Well, in this case, that P on the bottom is a -1 because it doesn't have another power, so it's -1. And then on top, we still have that constant K. And so being able to look at these formulas and say, what is my variable that goes in? What is the thing that changes? What's the power on it? And also, what's that constant that we're multiplying by is the key to power functions. Direct variation, power functions with positive powers. That would be like a 3x squared or pi times radius squared, something like that. Indirect variations are power functions with negative power. So we could have 5 over x to the 6th, could be on the bottom. Or we could have something like force equals k divided by d squared, so that force of gravity function. Anytime you've got something on the bottom, it's going to indirectly vary when that power is on the bottom. You're going to have something that indirectly varies. Something we could do with this, we could take a statement and write it as a formula. So the volume V, so that's one of our variables, we're going to identify that, of a circular cylinder with a fixed height is proportional to the square of its radius r. So we've obviously got some variables going on here. So volume is proportional to the square of the radius. So I know I've got an r squared here. My volume is proportional to my radius squared. And so my volume is equal to my k times my radius squared. The next problem that we have is the speed of the current in a whirlpool varies inversely excuse me, with the distance from the whirlpool center. So we've got speed, so S. We've got varies inversely, so indirect, with the distance from the whirlpool's center. So my speed varies inversely is going to give me distance from the whirlpool center. My distance varying inversely is that it goes on the bottom. So it's speed equals k over d. Okay, so varying inversely means that it's going to be an indirect variation, an inverse variation. So we've got that on the bottom. Let's look at a couple of graphs. State the power and constant of variation for the function, graph it, and analyze it. So if I need to state the power and the constant of variation for the function, graph it, and analyze it, notice, does this equation here look like a power function? Well, right now it doesn't, because we don't have it as something to a power. And so we're going to have to be able to rewrite these equations a little bit. So what I'm going to do is I'm going to rewrite this one as f of x. And I need to write it as x to a power. Well, 1/3, so the power 1/3 is cube root. And so now I can write my power as 1/3. My constant of variation, so this is COV, is going to be the number out front of x, the coefficient. The coefficient in this case is 1. When I go to graph this, and I'm going to pull up my little calculator here, my Desmos graphing calculator, you can use your TI-84. If I do f of x is equal to x raised to the 1/3 power, see what happens. Now, x cubed goes like this. X to the 1/3 is going to be that sideways because they are inverses of one another. So let me pull my sheet back up here. Whoops. And so my graph looks something like this. And it's asking me a bunch of questions to the analysis, like what is the analysis of this? Well, if I know that this graph goes like this, what's the domain? Meaning, what are the x values that it covers? Well, it goes from -infinity to infinity. My range is also -infinity to infinity, because this graph would keep going this way. It would keep going this way. And so it would infinitely go up and down. So eventually it'll get there, wherever there it is, infinity. Continuity, notice I don't have any sort of limitations. So my continuity is continuous. There's no discontinuities. Increasing and decreasing behavior. As I move to the right, what is the general trend of my curve? Well, as x moves to the right, meaning x increases, y also increases. So it's increasing -infinity to infinity. Symmetry. Well, let's see what we've got here. It's not symmetric with respect to the y-axis. It's not symmetric with respect to the x-axis, but if I took this and I flipped it over y, okay, so I just flipped this piece over y, and then I flipped it over x, what would happen? Well, it would go to the part of the curve that's in the third quadrant. Well, what that means is it has origin symmetry. So origin, both x and y axis, which means what? That means it's an odd function. Okay, boundedness. That means is there a value above that it doesn't get above? Is there a value below? It's not bounded. Because we can see that it increases to all values of y. It increases to all negative values of y. Local extrema. Are there any, mountains or, valleys? There are none. No local extrema. So there's no local extrema here. And so we see because there's no turning points, there's no maxes or mins, that there's no extrema on this graph. As far as asymptotes are concerned, because there's no bounds, there's no breaks, there's no breaks in the continuity, there are no asymptotes for this problem. Somehow I switched from this purple color to this blue color. Hope that doesn't bother anybody. End behavior. We started to talk about end behavior last chapter, and how do we define that? So this notation is going to be not something brand new, but we haven't explored it a lot, but it's something that we're going to look at going forward. We want to talk about the limits. So the limit as x approaches, so as x goes to negative infinity, the cube root of x, so the limit as x goes to negative infinity of the cube root of x is equal to negative infinity, meaning as x moves to infinity, the end behavior, this goes to negative infinity. We want to talk about the other end as well. So the limit as x goes to infinity of the cube root of x is equal to infinity. And this is where we have to have an understanding of domain, we have to have an understanding of range, and we need to have an understanding of this end behavior. So as the limit, so what's the highest limit as x goes to infinity? There is no limit, just keeps going. Okay, let's look at this second example. Once again, like we did first, we need to redefine this so that I can have it in a form that's going to tell me the power and the constant of variation. When I've got squared on the bottom, that means x to the negative 2 power. So the power is negative 2. My constant of variation, meaning the coefficient out front, is still 1. If I look at what this looks like as a graph, I'll just go ahead and redefine this bad boy here. Okay, so x to the negative 2 looks like this. What does that mean? Obviously, looks like we've got an asymptote here, looks like we've got an asymptote here, and so our answers to this analyzation are going to be a little bit different. So it looks like this. Do my best here on this drawing. That's not bad right there. That's not bad right there. I put that one in the books. Okay, so we've got this this graph here. As far as domain is concerned, what is the domain of this? Well, what x values does it touch? Obviously, down here, it keeps going to negative infinity. But then it gets to this 0 area, and it makes sense because 0 can't go on the bottom. And so my domain, it goes all the way up to 0, but it doesn't include 0. But then it continues, not touching 0, but going into infinity. If I look at my range is what y values does it touch? Well, there's no limit on the top. It continues to go up and up and up and up and up and up and up. Okay, so my range at the top is infinity. On the bottom, what is it getting close to? Well, it's honing in on 0. So 0 to infinity is my range. So let's look at continuity. Well, obviously, I have to pick up my pen to draw this curve, but where do I pick it up? So if I start here at negative infinity for my domain, and I keep going, obviously I have to pick it up at x equals 0. Well, how do I say that? Well, what we'd say is there's a discontinuity, and it's an infinite discontinuity because it goes into infinity at x equals 0. So an infinite discontinuity at x equals 0. So let's look at increasing and decreasing behavior. Obviously, as x moves to the right, so as I move to the right on my curve, this part is increasing. So as x moves to the right, my curve is going up. So I would say increasing from negative infinity to 0. But once I get to 0, so this is going up and up and up and up and up. As I'm moving on this part of the curve, however, as I'm moving to the right on x, what's happening? I'm going down. And so I'm actually decreasing from 0 to infinity. That's my increasing and decreasing behavior. Symmetry. All of these points, boom, 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 are reflected over the y-axis. So it's y-axis, which makes it an even function. Okay, boundedness. It is bounded below. And as we've talked about boundedness before, it's a boundary where it doesn't go anymore. So above, it's not bounded above because it keeps going, but it is bounded below because it gets to this 0 threshold and it can't go below that. Local extrema, we don't have any in this one. Okay, there's no places where it's, changing over to another one, changing over to increasing versus decreasing. Asymptotes, we do have 2 in this one. Because we have this x on the bottom, we know that we have an asymptote at x equals 0. Okay, so at this x equals 0 line, there's an asymptote, and also at y equals 0, because that's that line where the graph can't go below. All right, so let's write some limits. We want to talk about both ends. So the limit as x approaches negative infinity, what is it doing? Where is it going? Where's this graph going? As x goes to negative infinity, so as I march along this into negative infinity, what am I getting closer and closer and closer to? Well, I'm getting closer and closer to 0. But the way that I write that is the limit as x goes to negative infinity of 1 over x squared is, is 0. The limit, and now let's talk about the other end. The limit as x goes to infinity of 1 over x squared is equal to, let's analyze this graph. As it marches into an infinity, where does it go? It's going towards 0. So the limit is the same on both ends. It's going toward 0. So that's graphing and analyzing a function.